as a collection of tables. If you had a real database, you might even keep it in a database, but here you would keep it as a collection of objects. But think of that as a unit, and you can think of then the GUI as something that displays that, and the kind of net system as a bit of a controller. And of course, there might be some communication path through here. But if you think of it in this way, you can almost think of it as just a really big version of the same game project. Okay, it's almost just a really big version of that. And a lot of the design techniques you thought about for that are probably applicable to this. Just something to think about. Another thing to think about is to program defensively when you're doing the network stuff. Do not assume that anyone connecting to you on that port is really a Gnutella client. Okay, so, and don't assume that anyone that you connect to is really a Gnutella client. Even if, so program your protocol defensively, which means that, for example, if you are waiting for them to send the kind of greeting, which is a text string followed by a new line, okay, a natural thought would be to use read line to do that, since that reads a text line followed by a new line. But what happens if the person who connects to you doesn't send a short message in a new line, but sends 1,000 or 100,000 queues and then a new line? What is read line going to do under those circumstances? Is it going to time out or get sick of collecting queues after a while and throw an exception? Or is it just going to accumulate queues someplace until the connector finally decides to send a new line? And if so, is it going to eat up all the memory in your machine? And is that a potential denial of service attack on your client? So when you're doing the network programming, be paranoid and program defensively. Final thought is to make sure you keep straight the thread structure and thread architecture of the thing you're building, and kind of the class and data architecture and module architecture of the thing. They are, of course, related, since the threads use the classes and vice versa. On the other hand, they're different too, because there's, the threads, the splitting the thing along the lines of threads and kind of conceptual processing, and splitting it along the lines of kind of objects and modules is often different. So just keep in mind and be aware that those two are different things. Today's topic, I guess, is going to be object-oriented programming in C and C++. And although Java is currently alive and well, and is actually quite vibrant in the web server area, in a lot of other areas of programming, particularly client programming or shrink wrap, or a lot of anything that is performance critical, C and C++ is still very important, if not the majority of things, and it's an important thing to know. So today I'm going to try and talk about how to port the ideas that we talked about in object-oriented programming and basically good programming practice from Java into C++ and C. And I want you to come away convinced that you don't need the language facilities that Java gives you to write good programs, and that you should write essentially in the style you write in Java, no matter what language you program in. So let's see. Historically, C came first. C was developed in the 70s at Bell Labs to do operating system programming. And then much later, C++ was developed, essentially adding on a object-oriented programming layer onto C. Now, since we're coming from a background now of object-oriented programming and Java, that seems natural, so I'm going to work backwards. First, talking about what's different between Java and C++, and then how to port this thing, port the concepts down to say, programming in raw C, which is essentially stone knives and bear skins, where you have nothing done for you. So let's see, C++. There's a lot of stuff in C++, and I'm only really going to talk about the stuff that's relevant to taking programs that you've written in Java, or thinking about the way you think about writing programs in Java, and then convert that to C++. There's a lot of arcana in C++ that I will postpone until the end and just mention in passing. The good news about C++ and C is that the syntax you learned in Java almost entirely ports. Okay, the C++ syntax was built on the C syntax, and the Java developers pretty much ported that verbatim. So your variable declarations, your loops, your while loops, your for loops, pretty much all of that, your procedure calls, all of that pretty much works the same. It just ports almost verbatim. You could almost write a Perl script to convert Java programs to C++ programs. Some differences. C++ and C allow global procedures. As we saw in Java, everything had to be inside of a class, even though there was no particularly good reason for it being inside of a class. In particular, our main methods had to be inside of a class, and all of the math utility library routines were inside of the math class, even though they were all basically public static methods. Well, C and C++ allows you to define procedures at the top level outside of any class, and these function essentially the same as public static procedures, public static methods in Java, except you don't need to refer to the class around them. So a good place to start with any language is Hello World. And so Hello World in C++ and C, there's a large overlapping subset. /n, and that's an R. That's it for
Can you read them?
C++.
No, can you read the 3 lines?
Okay. Well, let's go through them. Starting from the top, the first is actually a compiler directive. Okay, the sharp includes include these .h files. It just basically tells the compiler to expand these .h files inline. Okay, so this is one difference between C, C++, and Java, is that in both languages there's a tendency to separate out the declarations and definitions of your classes, of your methods, and of your procedures from the implementation. Okay, in Java, you basically define the class, you define and you implement the procedures inside the class. Okay, in both C and C++, you separate the definitions, okay, which are just the method signatures, what arguments they take, what types they return, or in terms of the classes, what are their instance variables and what are the methods of the class without implementation. So you separate those two, and the definitions are usually put into what's called header files. And header files in C and C++ usually end in .h for C files, Some people use .hpp or .H or .hxx to indicate C++ files. These are just conventions. There's no particular meaning associated with that. It's just a convention. The angle brackets just mean that this is a system level header file, and go look for it in where you find all of your system files. And what this particular one is one that you almost always include. It's the standard I/O library. C and C++ have or C anyway, has a much more limited and basic I/O library than Java. It doesn't have the 60 classes that give you all of the I/O facilities of Java. It has very, very basic stream facilities: read, write, open, close. And all of the definitions for those routines are in stdio.h. This is not the same, or not even analogous to, the Java import. Okay, they're really doing very different things. Okay, the next thing we have is our procedure declaration. It's at top level, and we start executing once again at main. Main is always the magic procedure name in C and C++ for where you start executing, unless you're using some variety of Microsoft Windows development environment, in which case Windows actually writes the main somewhere in library and calls some other function, which depending on the libraries you're using is different, often called winmain. But if you're writing in Unix, certainly you always start at main. Main returns an integer in C++, though you can ignore it, and that integer is an error code that gets sent back to the operating system that you can use to say whether your program successfully completed or not. The same thing as we saw in Java, we passed in command line arguments in an array of strings. And we're doing the same thing here, except that since C and C++ don't have native string objects built in, we have a much more primitive thing here, which I'll talk about in a bit. Finally, we just print hello world. Printf is a formatted print utility that's defined in here. And it works pretty much the same as println in primitive cases, except you have to add the new line yourself. The /n is a new line. It also has wonderful formatting capabilities. So you can, by putting various escape characters in this format string and passing in arguments, have it print floating point numbers or decimal numbers, and you can control the format of them. Java has a format object which does all this, but printf is extremely convenient for doing this. And printf has a cousin, scanf, which does this in reverse. If you have a line of text that you know consists of 3 integers, or maybe an integer, a string, and an integer, it has a way of very simply specifying that's what you expect. Here's where I want you to put the things. Just read that line and do the conversion. So in some ways, it's much easier to use. OK, to compile and run this thing, you would write something like, say we wanted to do it in C++. It's, I said, both a valid C and C++ program. The C compilers are traditionally called CC. There's the GNU C compiler, which is called GCC. These vary from system to system. C++ compilers are variously named. The GNU one is called G++. Sometimes they're called C++. Sometimes they're called CXX to deal with systems that don't like pluses. Sometimes they're probably not called CPP, since CPP probably means something else. But say we're using the GNU compiler, so we do GNU++, and say this was in a file called hello.c, or hello.c++, we would type something like Okay. The source files for C are usually ended with a .c suffix. For C++, you can end them with a .cpp or a .C, or there's a variety of conventions. Some people just use .c, but I find that a little confusing. So this will run and produce two files. Okay. Unlike the Java compiler, which converts java.java to .class files, it's purely a compiler. G++ in this configuration is doing two things. It is compiling, meaning turning our source files, CPP, into object files, and the equivalent of .class files essentially is .o files for object. These are now binary machine code files for the particular architecture. Unlike Java, C compiler output is not going to be portable in general from architecture to architecture. So it does this compiling step, okay, and then it does a linking step, okay, which takes all of your .o files, hello.o, any others that you might have specified, any libraries, what's the standard library, libc.a, combines them all into an executable, a program you can actually run. All right? And this -o basically tells it to put the output into a file named hello. So the final output of this stage is a executable file called hello, which you can then simply type at the console window, hello, and it'll print hello world. Okay? So a little different system. You don't have to invoke the Java runtime as you do in Java. The -o just tells you what the name of the final executable you want. In general, if you don't give it a -o option, it will put it in a file historically named a.out. Okay, that's the default, usually the default output file of the C compiler and linker. Anything else interesting about this? I guess not.
What are the letters before the final hello?
Oh, this is libc.a, as well as any object files, and you can link more than one object file. You can make a bunch. It also will go and find any libraries, which are kind of equivalent to the Java class libraries that you get, but there's a number of them that come standard in the system. libc is the default one, which has the runtime and the standard I/O library. There's also libm, which has the math functions. And then if you start to use stuff like X-Windows or any toolkits like Motif, each one of those will add on more and more libraries onto here as you get them. So, okay, classes. How do we do classes in C++? Let's talk about defining classes. This is actually not too different than what we saw in Java, with the exception that we tend to separate the declaration from the implementation. So say we wanted to go back to our original example, our 2D vectors, we would make one file called vec2d.hpp. Let's do that. And this is going to have our class declaration in it. And it looks pretty much the same. vec2d. And one slight difference is in the way you specify the access descriptors. Instead of putting them in front of each thing as a keyword, you tend to put these little labels in there, which say that Okay, everything following this private thing is considered private until you then put like a public colon or something else. Okay, it's kind of unfortunate syntax, but harmless. So remember we had our two variables here, x and y, just as before. And then we have some public methods. And just as before, we have a constructor. And let's just add one more, which is length, which, oops, this actually returns something. This returns a double length double x double y. Okay. So pretty familiar, not a big stretch from what we've seen, except we've only declared them. We have not implemented them. All right. So now to implement them, any questions on the declaration?
Length takes arguments even though we think we're going to take them from
Ah,
our own pattern.
you're right. No, I'm sorry. This is just absolutely wrong. Just getting carried away with writing. That works exactly the same as it would in Java. So length is just an instance method. Okay, so we would now do our implementations. So we'd make a file probably called vec2d.cpp, but it doesn't have to be. It could be called anything. C++ is much less fussy about what you call your files with relation to what you call your classes. As a matter of fact, it's completely agnostic. It does not use the name of files. It does not relate the names of files to the names of classes in any way. So I could call this lecture17.cpp, and everybody would be just as happy. So now I have to implement these guys, my constructor and my length function. And you would do it as follows, pretty much the same as you would in Java, except, let's pass these in, call these xx and yy, just to avoid. So then I just do x equals xx, y equals y. And that's pretty much the same. Similarly, vec2d : this is double. When I write C++, I tend to, and this is just me, well, actually a lot of people do this, put the return type on the line above the actual name of the function. And that's basically so I can scan through a file and always find the name of the function on as starting at the first character. But it's just a convention. You could just as easily put that out here. All right, so length, and I access, again, instance variables just the way I would in Java. This is return x star x plus y. Actually, I have to put a square root in there, don't I? Square root of x times x plus y times y. Match up to there. Okay, square root sqrt is something that's nicely provided to you by C in the math library. So, but this is it. So a couple differences you notice. There's no big class wrapper around this thing. Okay, so that presents a problem of how do we know that the length routine or length routine that we're writing here, the length method, is the one for vec2d rather than the one for something else. And for that matter, how do we know we're trying to make a constructor here rather than simply a vect2d method on something else? And the way that you do this is this colon operator. Okay, C++ syntax loves the colon. This colon is a scoping operator, which basically says that this is the length. We're defining the length method on the vect2d class. Okay. Similarly, this is the constructor for the vect2d class. You can use colon also to call static methods in classes. C++ does have static methods in classes, even though you can put static methods at top level also. By using this similar to the way you would use dot in Java. Okay, so you now can go and compile this up, and using a command analogous to this. Of course, we don't have a main, but you can nonetheless produce a .o file by saying G++, and there's a magic flag that says just produce a .o file, and give it this, and it will compile it up. Now we want to use classes. Yes?
These are in two separate files?
These are in two separate files in C++ traditionally. Now you can, okay, you certainly can implement these methods inside this file, it turns out. Inside the .h file, you could build exactly what you would build in Java and put the actual definition of the, put this code in here instead of just ending with a semicolon. You would do an open just like you would do in Java. Okay, that puts everything in the .h file and nothing in the .c file. The advantage of doing that is that the compiler then can, when people are calling these functions, it can get smart and inline them. Okay, it can say that I know this is a function I want to go fast. It's a small function. I'm just going to not even do a procedure call. I'm just going to expand the code for this function in line, and thus it doesn't have to pay the overhead of the procedure call. So moving your implementations into the .h files lets the compiler do that. And oftentimes you might want to implement your accessors and mutators, which are usually very small and uncontroversial, implement them in the .h files, and very simple constructors maybe, so that they can be expanded inline. The reason for separating them is that anybody who uses the class, anybody who wants to use the class, has to include, using this statement, the .hpp file, so it knows basically what the structure, what the interface, okay, of these classes are. You can think of the .h files as being equivalent, almost, not quite, but analogous in some ways to a Java interface. It tells you what the signatures of the functions are without giving you any implementations. And this is what anybody who uses that class has to include. Now, if you have the whole, and this is what you typically ship, you have to ship in text form with your library. Your library is all compiled and contains the implementations, but you have to ship these in text form so people can know what the signatures of the things they're trying to call are. Okay? Java kind of sweeps some of that under the rug by groveling around the class files for interfaces at runtime and compile time. Here, these binary libraries are all in machine code, so you can't extract the signatures. You need these text.h files. Now, if you expand all of your implementation in the .h files, certainly it all works, but then you're shipping your source around, first of all, in text form, which is, makes all these .h files large, and it also is a version nightmare in that if you fix a bug in your implementation, you've got to then ship it out to everybody, even if it doesn't affect the definition. Okay, say I had implemented length wrong. If I just had it in a C file, I could fix it here and ship a new binary library, as opposed to having to get everybody to recompile all of their code because I expanded it in my .h file. So that's why people typically split this up, and you put your interface in the .h files, your implementation in the .c files. The only exception is when you really want something to be inlined.
And if you have multiple classes, can you do all of the declarations in one file? And then
You can. You typically don't, but there's nothing in the compiler that will prevent you. Yes?
We need to sharp include the .hpp file here.
You're probably right. Even in here, since it needs to know these and it's going to error check for you, we probably need to do this. vec2d.h. Yeah.
I thought that's what the first vec2d was doing.
Oh, no.
Was finding the file.
This.
No, sorry. When in those.
Oh, this says it's finding the class. But unlike Java, there's no mapping between class names and file names.
Right.
So you have to tell it, the file explicitly. And it includes double quotes and angle brackets mean almost the same thing. Angle brackets mean search the system directories first, or search the system directories. Double quotes means only search my local include path. I tend to use them conventionally that anything the system provides or foreign libraries provide, I use angle brackets. Anything that kind of my system that I'm building, I use the double quotes. But they're pretty much 90% interchangeable. All right, so how do I allocate one of these? Well, I can do vec2d v1, and that allocates one. So here's a big difference between Java and C++. Okay? In Java, all class variables are essentially references. Well, they are references. So when you say, if this was a Java statement, what this would do is essentially allocate space for a pointer to a vec2d on the stack and initialize that to null. And then I would really, to initialize it, I would have to say vec2d v1 equals new vec2d and call the constructor, right? This is the form we're familiar with. C++ will actually allocate classes on the stack. Okay, so what this means is not only do I have this v1 variable is not a reference to a class, it's not a reference to a vec2d class, it is a vec2d class. The memory, okay, for the vec2d class, these doubles, is actually going to be laid out. If we look at our stack frame and we allocate a new thing, it's actually going to be laid out on the stack. Okay, so this is actually creating space on the stack and putting the memory for this kind of right here, you can think of it as. Why do this? Well, stack semantics are very nice. Okay, a lot of times your storage management follows stack semantics, which means you call into a routine, you need to allocate some data, you operate on it, and then you return from the routine, and all the data that you needed to compute what was in that method went away. Okay, very nice thing about stack allocation and semantics. And one of the key differences, another key difference between C++ and Java, is that C++ and C are not garbage collected, which means that you have to keep track of every bit of storage by yourself, by hand. All right, so naturally allocating stuff on the stack is nice because the stack automatically allocates and deallocates automatically, so you don't have to worry about, cleaning up that storage because it's just on the stack, and the stack system does it for you. Okay, say we wanted to call, this is just going to call the default constructor. If we wanted to call our actual constructor, the syntax would be something like this. Okay, we just append the arguments to that variable declaration there, and everything is well. I'm pretty sure that's right. I haven't done this since November, and I've been doing Java a lot, so sometimes they all get muddled up inside. All right, so how do we call methods on this thing? Well, we use the Java syntax. Pretty much the same syntax. Actually, I can put that in a value even. I can do double length equals v1 dot length. And this will do just what you expect, but not quite the way you expect it. This dot is the same syntax as Java, but instead of referring to a reference the way it does in Java, it refers to the actual class, instance. So you basically use dot on an actual instance as opposed to a reference to an instance. We'll see how you handle references in a second. But that's pretty much how that works. Any questions?
So you're saying the syntax is the same?
The syntax is the same. The behavior is the same, but the way it's implemented is different.
So when it handles in Java the reference of an instance, it's actually performing, though, the method on the instance, isn't it?
It is, and I'll show you in a minute
How that does it.
how they're different. Well, here's the C++ analog of the Java thing. The difference is that in Java, the actual storage would be allocated off the heap, and you just have the reference here. Here, the actual storage is allocated off the stack. Okay? And that makes a difference only from the point of view of storage management, and that's something you always have to have in mind. Now, C and C++, unlike Java, have explicit pointers. Okay? In Java, we said all these things are references, but we can think of them as classes because we're not allowed to really do anything with the fact that they're pointers. We're not allowed to do nasty pointer arithmetic like we are in C certainly, and C++ if you try hard enough. So the syntax for pointers is you add a star to something. Okay. So vector2d star v2, this means that the variable v2 is not a vec2d instance like this v1 was, but it contains a pointer to a vec2d instance. And here I've initialized that pointer to null. Yes?
If you're calling a function
Yes?
and you're expecting, say, a vec2d return,
Yes?
and so the new function allocates space in the stack for new vec2d, does whatever it does, and then returns that vec2d.
Yes?
And so that's somewhere up here on the stack, and the space you're expecting to put it is down here because you called it there from there.
If it's a return value?
Well, what happens to how does the function down here on the stack that called this new function that's built up the stack and created a vec2d up here? How does it get this section of stack that represents vec2d back?
If you pass classes, okay, real class variables, everything, if you just pass it by default, it's passed by value. Okay, so by default, everything is called by value in C, which means that if you pass a class instance, not a reference, but a class instance, like v1, it will actually make a copy of that whole structure on the stack for the new arguments. And therefore, if you change any portion of that, it will not get reflected in the thing you passed in, because it's totally new memory on the stack. Similarly, if you have a return value of a thing is copied back, of a reference is returned by copy as well.
In the case of our constructor, if we're building a new copy on the stack of our vec2d, and we construct it in that copy, but we're not changing the x and y of the original, aren't we essentially losing what our constructor's doing? Don't we somehow have to get it from that new copy to the original?
No, the constructor will do the right thing. It will first allocate it on the stack, and then it will call the constructor on that version that's on the stack. So it will make it work. right. For exactly these problems, there are,
I guess maybe a mutator would be more appropriate, because with the constructor we didn't have one previously.
Right.
But if we wanted to change
Right.
X and Y,
right.
we're going to have
So there's two ways to do that. One of which is this way, okay, which is roughly equivalent to what Java does. So this is a pointer to a vec2d, which we're going to initialize to null. C and C++ use null as all caps, not null as smalls, a gratuitous difference. And to get one of these, we do v2 equals new vec2d of okay, vec2d equals new of that. And this is roughly equivalent to the Java version of vec2d v2 equals new vec2d. Okay? The difference in C is we explicitly have to say it's a pointer. It's a vec2d star. And some people put the star, like I do, next to the vec2d to make it look like it's a vec2d pointer type. Some people will put a space here and the star next to the v2, and some people will put a space here and a space there, and it doesn't matter. I really like that convention, but that's just me. So what this does is it makes pointer on the stack, allocates a structure or a class instance off of the heap, and puts it in v2. And now to do a method call here, we need to use pointer syntax. Len equals v2, and we do this little arrow thing, which is a dash followed by a greater than length. Okay? So this computationally is doing the same thing as this, except that in this case it's allocated off of the stack. In this case, it's allocated off of the heap, and we allocate it with new. Okay. Some other things that come up. Now that we've allocated this guy, and there's no garbage collection, how do we get rid of it? Say we decide we've gotten the length of it, and we're done with it. How do we get rid of it? Well, if we just ignore it, like we do in Java, it won't go away, and as our program runs and runs and runs, it'll gradually accumulate stuff on the heap that we've allocated and haven't deleted, so our heap will grow and grow and grow, and our memory footprint will grow and grow and grow, and if we run long enough, eventually we'll run out of process memory and crash. This is known as leaking, and is a big problem in C++ programs because it's hard to catch everything. But there is a command to get rid of things, and that is delete. Okay, this is a keyword. It's the opposite of new. So we say delete v2, and that deletes the instance of vec2d that we made on we allocated from the heap up here. So in C++ programming, wherever you have a new, you somewhere in your program have to have a corresponding delete. Okay. Now there's an additional problem with storage management in that delete doesn't know anything except the size of the structure. Okay, it sees class vec2d as a chunk of memory that's the size of 2 doubles. So when you call delete, all it's going to do is delete 2 doubles. So what happens if in our constructor we had another pointer to some class here and allocated something else off of the stack? Okay, so say we had, I don't know, another vec2d star here, and we had done an allocation of new. When we call delete on this guy, it's going to say, okay, I've got 2 floats and a pointer. That's for 12 bytes. I'm going to delete, restore these 12 bytes back. But this thing that it points to is now dangling. It's lost. So this is a potential problem. And in order to address this, C++ has a opposite of the constructor function called the destructor function. And the destructor function is like the constructor, has a canonical name, and it's just the class name with a tilde in front of it. Okay? So whenever you have any non-trivial structure that has anything except basic data types in it, you need not only a constructor, but you need a destructor. And a destructor is where you put all of the cleanup stuff. For example, if I did allocate some heap storage inside in the constructor, or maybe even during some of the methods, what my destructor has to do is go through and check on all the things I might have allocated, and if I did allocate something, call delete on that. So delete, when you call delete on a variable, before it cleans up the space, it will call the destructor on that instance, and that can call delete recursively on its submembers, which will call the destructors of its submembers. So whole big data structure trees can be cleaned up this way. This is also a good place to clean up if you've done any locks or allocated any resources or maybe opened some files. The destructor is your last chance to clean up. So if we allocate something with new, we can call delete on it. What if we've allocated something off of the stack? It just goes away when the stack frame returns. Well, kindly, C++ will also call your destructor when the stack frame returns. So it's going to call the destructor whenever an instance is going to be destroyed, which is a nice property.
Is there any reason why you would ever delete without destroying?
Well, delete always, inside delete, it always calls the destructor.
Oh.
So it's automatic.
Oh, okay.
The destructor just tells delete what to do. One thing that's also good to do after you call v2, after you call delete on something, is always set it to be null. Because delete, although it essentially gives the storage that this guy was pointing to back to the heap, it doesn't change the actual pointer value in v2. So you're then pointing to something which has no validity. And then if you go and do future method calls on v2, something very strange is going to happen. Because potentially some other class could have allocated that same storage and written stuff in it and reused it, and now you're like going into it and you're saying compute the length of this, and the code is still there, so it's going to grab two random values and give you a length which is going to be meaningless. So if you delete something, it's best to null out your pointers, so at least if you use it here, you'll get a segmentation fault, not a wrong answer.
So I guess you're just convinced that garbage collection is good today.
Garbage collection is good for the programmer, not so good for the user. Okay, it's much, much easier to program in Java with garbage collection since you don't have to keep all the stuff in mind. And if you start to allocate something in one variable and then share it between three and store it in another structure, it becomes very complicated to figure out and to remember when you can destroy it, when there's nobody out there who can use it. And you have to do all that by hand, and it is a substantial part of the difficulty of writing good C++ programs. On the other hand, once you do, the program is running a lot faster because you don't have to stop periodically to do some mark and sweep garbage collection over your storage, or when you're copying things around, you're not incrementing and decrementing reference counts and all of that. You can implement some of that in C++ if you like.
Are there any kind of IDEs similar to Forte for C++ that would do that kind of debugging and say, you've still got something out there using this?
There are IDEs, certainly, Visual C++ from Microsoft being the one that really comes to mind. There's also a utility out there called Purify. I think there's a commercial program that will run over your program and tell you whether there's any potential memory leaks. It's good. It's not perfect. It will often complain about lots of stuff that isn't real, though it typically catches everything that is real. So if your program does go through Purify, it probably doesn't have any leaks, though if it doesn't go through Purify, it could still not have any leaks. The thing I wrote this fall will not go through Purify, but it will run indefinitely without leaking. So what's next? Yeah.
This setting your pointer v2 to null.
Yeah.
Do we have problems with pointers just hanging around? I mean, does that truly get rid of it?
Well, what it does is it just sets that variable to 0, essentially. So it keeps you, if you do try and use it again accidentally someplace else in your code, you'll try and access instance variables off of 0, which is going to, it's going to basically crash your program, but it's not going to produce a wrong answer. So, but yes, you can get into boundless trouble by reusing pointers after you've deleted the thing they point to.
We don't have a way to uninitiate or to get rid of the pointer so that...
Well, you can pop it off. You can make whatever function this is scoped to return, right? And then all the references go away. But say, it's just very easy. When the first time you do it, it doesn't tend to happen. But then when you add something down here and subtract something up here and move stuff around, you tend to forget all the preconditions. And or some branches in a big if statement or loop do the delete and others don't, and you get this bug that happens 1 out of 100 times, and it's just not fun. Okay, inheritance in C++. How much time do I have? Is pretty much works the same as inheritance in Java, with the exception of the syntax. Say I wanted to do my class complex as we did, that inherits, that extends vec2d. Pretty much the same syntax, except that instead of the word extend, you use a single colon. And you usually want to put this public here, which means we are only making the public methods accessible to the child class. So then this pretty much works the same, almost the same as it does in Java. You can override methods from the source class, and you can, from the parent class rather, and you can add new classes to complex that weren't on the parent class and do all the stuff you did before, and everything pretty much will work the way you expect, porting your notions over from Java and fixing up for this syntax. I think that's all there is to say about that. Yes. Unlike Java, multiple inheritance is allowed, and so you can list things with a comma here. One other thing that's different is you do not to call the constructors of your parent class, you do not call super. There's a number of different syntaxes to call the constructors of your parent class. They're all pretty horrific in my opinion, so I'm not even going to mention them. But if you find yourself having to do it, get the C++ reference manual and fight your way through it. Okay, one other difference between C++ and Java is you don't get polymorphism by default. Okay, inherited methods in Java are all polymorphic in that you can do that trick we did in problem set 1 with declaring rfunc to have this evaluate method, declaring lots of subtypes of rfunc that actually implemented evaluate, and then we would allocate one of these things and write some algorithm like our root finder in terms of rfunc and call evaluate on rfunc, and it would always go down and do the right thing. By default, C++ does not do that. It does not do that by default for reasons of efficiency, in that polymorphic routines are less efficient and more difficult to inline than non-polymorphic routines, and you don't always plan to use it. If you do plan to use polymorphism, you have to declare in the parent class the method that you want to be polymorphic. Okay, this is the child class. Where is the parent class? I guess I erased it, but go over here, say we had class vect2d. We would have to declare our method virtual. Say, I don't know what an evaluate method would mean, but say we had an evaluate method that we wanted to be different for all of our subclasses. And I probably need a type here, so I'll just make it int. So we call it virtual int evaluate. And basically this says that I want this method to behave in all of my subclasses to behave polymorphically. I want to be able to use polymorphism on this routine across all of my subclasses. Okay? And we had, in the case of problem set 1, we wanted to make these abstract polymorphic methods that we didn't want to define them on the parent class, but nonetheless wanted all the child classes to be able to use them and everything to work. And the way you do that, that's called in C a pure virtual function. And you do that by, in the class, in the .h file, the class definition, just setting this to be 0. So the bottom line there is that polymorphism isn't there by default, but you can get it. If you make a class full of nothing but pure virtual methods, okay, this is something that gives you full polymorphism but no implementations. This is equivalent to either a pure abstract class in Java or an interface in Java. And so you could use that as, say, a entry for one of your multiple inheritance. Multiple inheritance of many classes with many different data members in each class gets to be very complex, because what if some data members have the same name? How do you resolve which one is really the one you see and all that? And so the common wisdom is it's best to stick to single inheritance of anything that has actual data members in it, and multiple inheritance for classes that only have methods in them, okay, essentially interfaces. Some people do not like that system, but I found it to be the safest thing. Okay, almost finished with C++. We have a couple just Arcania things that I'll mention, but I won't go into any detail on. One of which answers the question that somebody brought up of how do we do mutators and constructors and the like conveniently. Well, one way is certainly to have them operate on an actual reference. So you have the thing point to a function, but C++ actually implements for things like that call by reference, okay, as well as call by value. And call by reference is a kind of squirrely concept to get your head around, but I'll just mention it. Let's see. So say we have, I'm going to erase this and start from scratch. Say we have some class that we allocated off the stack, v1, and say we had some method, or not just a method, just random procedure call that we wanted to be able to alter the properties of that. One way to do this would be to pass into my alter. Let's make a function called alter, and have it take in a vect2d star, call it v, and say this is going to be, just do v points to x equals 0. It's just going to set the x component to 0. And note this will only work if x is public in v, and it isn't, so it won't work in this case, but the principle is the same. So what we can do here is I can't call alter on v1, since v1 is a pointer to a vec2d, and this is a vec2d, but the syntax to do this is ampersand v1. This is standard C syntax. That's supposed to be an ampersand, which means take the address of this structure. So basically it finds this class instance, takes the address of it, turning it into a pointer, and then passes it into here, and this guy treats it like a pointer and everything as well. This is how you would do things in C. C++ adds another wrinkle on it to handle a number of things having to do with constructors and returning things. Let's say I make an alter 2. And the syntax is you move the ampersand around. So you declare your routine, instead of being a void, a vec2d, you declare it to be a vec2d ampersand v. So this is reference to, and then you pass it with v1, and then you use the dot syntax here. Okay. What this essentially does is exactly the same thing I did before, is make the pointer, but it lets you use the dot syntax and make believe that you're copying it in and copying it back out, even though it's shared. So it's a tricky thing. If it's not clear, don't worry about it until you have to program C++. And indeed, you can get by programming in C++ without ever using it, without using it very much anyway. Another piece of C++ Arcania is templates. Templates are a way of abstracting algorithms and classes based on data types. So you can define an abstract data type and implement everything in terms of that, and then essentially macro expand at runtime all these algorithms by substituting in integer or double or whatever for this thing you made up. That's all I'll say about it. To my way of thinking, it's a nightmare. And code written with templates is very difficult to read. Another thing that C++ lets you do is override operators. Okay, it will let you override plus, as well as overriding, when you inherit in classes, you can override functions from your parent class, right? C++ lets you override all of your favorite operators, including the pointer operator and array access. And it actually, in some ways, even lets you override equals. Okay, so you can make up two classes and define what plus is going to mean when you add two instances together, and then use regular C, and it's the same as Java, expression syntax to do them. And if you make it do something intuitive, it might be good. And if you make it do something non-intuitive, like you can really do some screwy things by overriding array access and pointer access and stuff like that. Very powerful. On the other hand, I find it makes code very difficult to read.
To do that, you would simply define a method called plus.
There is a syntax for it. I think you have to say operator plus is the name of the method. But yeah, it works pretty much the same.
So you would define that. You would say that it.
Right, you would put in your
dot x plus the second dot x equals the new x, and y plus y equals y, and then you could just say vec2d new equals v1 plus v2. If you overwrote equals and plus, that would be really cool.
Yes, that's what you could do, and it is really cool until you get carried away. One way to write hello world, in fact, they override, the C++ stream library overrides the left shift and right shift operators on their stream classes. So you can also write hello world like this. Okay, and what this means, cout is a magic thing that is the stream. It's essentially system.out in Java. It's called cout in C++. And the shift operator is overridden in this class to be essentially println. Okay, so So instead of writing, c.out.print of that, you can just write c.out that and that. One more matter of taste is that in the newer versions of C++, kind of, I think, in response to the success of Java and the stuff in the java.lang and java.util, all those nice classes and data structures you get, like hash tables and trees and enumerators and all that stuff, iterators, there's a new library that's going around called STL, the Standard Template Library, which attempts to duplicate all that stuff. Makes extensive use of templates, and so reading STL code is, if you're not used to it, very unfamiliar, since it introduces a lot of angle brackets and colons and a variety of casting structures. It's also had recently, well, it's probably not ready for prime time in that it has some serious portability problems at the moment, and some people love it and some people hate it, and so just be aware that it's out there. There's whole books, like several hundred-page books on how to use the STL. All right, so let's drop back a little more. This is C++. What's different about C and C++? They're a lot the same, except in C you don't have classes at all. Okay, C is very basic, minimalist procedural programming language. You get functions and you get data, basic types, but you don't have classes, you don't have inheritance, you don't have any of that from scratch. But you do have structured data types, roughly the equivalent of, if you think of them as classes without methods. They're called structs. So struct, you could make a struct vector 2D with two members, double x, double y. All right, and you could use this analogously to the way you would use classes, except notice it doesn't have any methods. So in C, you have to work a little harder. You want to program exactly the same way as if you had classes and maybe even inheritance and polymorphism if you really need it. But you have to use self-discipline and build it all by hand. For example, in structures, all instance variables are often called members in C and C++. All members are public. So anybody who sees this structure definition can get at these member variables. So the trick is not to. Even when you define something like that, and this goes in your .h file, which everybody gets to see, you pretty much would always want to define accessors and mutators. And anytime this structure is used, you would always want to use only structure, only accessors and mutators, never touch the actual data. Or only in extreme circumstances when you have a very good reason to do so.
If you can't write methods, how do you get it to do that?
Well, you have to split up you have all these functions. You have to split them up in your mind into two sets. One in one file, which implement what you consider to be the methods of this class, if you had methods. Okay? And the rest of the program is the program that uses that class and can only access the structure through those methods that you wrote. Now, even though all those functions are kind of equal in terms of their access, in your mind, you're just writing it differently. You're writing it as if you had a class. All right? You allocate these things. You can allocate them off the stack, similar to this. You can say struct vec2d v1. That will give you one off the stack. They don't have constructors, so you have to initialize. It's better, I think, to do them with pointers. And unfortunately, you don't even have a new and delete. But you do have void2d star v2 equals a system memory allocation routine called calloc. And there's one called malloc. Calloc zeros everything, so I like to use it. And then you have to call it with this little macro called size of, which just tells it how many bytes to allocate. Okay, this is a very primitive routine. It tells it I want to allocate one thing of size 8 bytes. Okay, so it multiplies that by that, and it calls the system allocation routine and gives you a thing. Okay, so how would you emulate methods on this? Well, you have to do it by hand, but what do methods give you? They give you kind of a namespace associated with the routine, so it makes vec2d length different than some other structure's length. Well, that namespace issue you can do by hand by just using underscore or whatever syntax you like. You just have to do it by hand. Okay, you know what's going on in C++. You just have to emulate it by hand in C. The other thing that a method call gives you is it passes in the secret argument, which is the instance. Well, here, no one's going to pass in the secret argument for you, but nonetheless, you have a pointer to the thing you want to call it on. So now we can pass in. We've essentially emulated, in very crude form, a method call on vec2d. As long as we stick to this convention that we have what we're thinking of our class name underscore method name. Okay, we don't get any name conflicts. And then we just always by hand pass in essentially this. So whatever instance we wanted to call it on, instead of doing v2 dot length or v2 points to length, we just do length of v2. And then when we write the routine, okay, we have to take into account the fact that we're passing in a pointer. So we would have to do, we would have to declare a argument here, which would be vec2d star v, and then do v points to x times v points to x plus v points to y, v points to y. And, when you're implementing routines of this type, since they're conceptually your methods, even though they're just really global functions, you are allowed to access the variables directly. But anybody who's calling this guy from outside is only going to use these black box routines. Okay, so you're just building up that method infrastructure by hand. There's nothing magic about method calls, or nothing very magic about method calls. Inheritance is a little more complicated to do, but not too much more complicated to do. You just make all of these for your parent class and your subclasses, and call the one you want. You have to figure out in your program which version you want, which makes things a little more difficult. What gets extra difficult, though is still doable, is polymorphism. But you can do it. You can do it. It just hurts. Okay? The reason you can do it is because C and C++, unlike Java, allow as a legitimate data type a pointer to a function. Okay? So you can declare an arbitrary function like main or vec2d length. Okay? You just have this function code written out. You are allowed to take the address of that using the ampersand and assign it to a variable of the proper type. So now you can pass around a pointer to this function. Furthermore, you're allowed to do procedure calls through that function pointer. Okay? And so even though you just got some random function in this variable, you can call it, pass some arguments to it. Hopefully you pass the right ones, though you can never be sure. And, it will do the right thing. So then all you have to do is implement, using that mechanism, polymorphism. And to do that, you just need to know a little bit about what is going on in polymorphism.
Why would you want to do that in C rather than use C++?
Well, sometimes you can't use C++. Sometimes it's a management decision. Sometimes it's a portability decision. Sometimes you want to maybe implement C++ internal to modules, but have the interfaces to modules be in C. And if you want to implement polymorphism across that, you have to do it by hand. And if you start to think about distributed systems and systems where all the objects aren't in the same process, you essentially have to start to think about doing it by hand as well.
Is it a good idea to try to code in C as if you were writing in Java? Wouldn't it be better to write in a style that's natural to C?
No, I think it is. I think that the style we use in Java because it's good programming, except unless there's cases where we're forced into doing something bad by Java syntax. And it's good programming no matter what language you're writing in. It's good programming to use encapsulation, to hide your implementation from your definitions, from your interfaces. It's a good programming practice to hide, however you can, even the data members in your structure. And there are actually nasty things you can do to keep people from ever knowing what's in your structure and force them to go through your interface. So I think all the things we talk about abstraction, about encapsulation, about trying to make things maintainable and code reuse all apply to C. You don't want to go overboard, but to the extent that you can, you want to follow the same procedures. I would say that my C code and my C++ code and my Java code all look about the same, except for these syntactic transformations. So what's going on behind the scenes of polymorphism? Well, associated with every class, say in Java or with virtual methods of C++, there is, this is some data structure that's really telling you what's going on in the class. And part of it is what's called a virtual function table. Okay, so it's basically a big table of function pointers, just pointers to function code that you've written. And what polymorphic methods do, what every instance has, say we have an instance, okay, it has a pointer to what class it is when it gets created by new. And remember, even if we were in Java using this through some variable that was typed of a superclass, it always behaved as if it remembered what it was. Okay, even if we called something in rfunc that was really a polynomial, it would always get the right polynomial method. And the way it remembers it was a polynomial because it has internally, when it gets created, a pointer to the class data for polynomial. And part of that class data is, in Java, it's a list of all of the functions. In C++, it's pointers to all of the virtual functions. So what you're really doing when you're calling a method here called, say, eval, okay, this gets turned into compile time into third method it just gets turned into third thing in the virtual function table. All right. So it doesn't get bound to, at compile time, a particular piece of code. All right. What it does is get bound to an index into the virtual function table, so that if you call eval on here, on an instance of, say, that's a poly, it will run up and get the third guy, and it will call this function. Whereas if you have another instance that's pointing to totally different functions, and some of them could be shared, and you call eval on this instance, it's going to look up in this table, find the function, and call that. Okay, so that's kind of what's going on behind the scenes with polymorphism. And given the fact that you can store function pointers in structures in C++, or in C rather, raw C, you can pretty much build up all this mechanism by hand. Okay, what you typically do is not, unless there's a lot of them, you don't even bother to do this, but you just, in your structures, put function pointers. You just put pointers to the eval, to the various polymorphic routines you want. Okay, and then when you build one of these, when you allocate it and initialize it, you set these pointers up to be the right methods for that particular subtype, and then you can go and treat, pass pointer to this around and treat it as a pointer to something else. But when you go and call an eval routine on it, it will always go to the right place. Okay, because it's just looking up in some table and then grabbing the pointer out of that, and then passing the arguments through this function. It's a bit hairy, but it does work, and it's actually kind of neat. Let's see, is there any other thing to say? I guess the only other points are C has an even less substantial library than C++. It basically, you have the standard AO library, some math libraries, in some cases a thread library, and then just very system-dependent things. Maybe some associated with X Windows or other ones associated with Windows, but those start to get very system-specific and non-portable. So if you want to stick to portable C, you've got a very basic set of capabilities, maybe 50 function calls in the library.
Is there a GUI in C and C++?
There's no native GUI in either C and C++. Since in Java, the GUI is kind of the same as the language. They're mixed in together. In C++ and C, they're separated, so you can write and talk to there's lots of GUI interfaces for C and C++, but they're different from the language. So, for example, Microsoft Windows gives you both a C API and a C++ API for basically running Windows apps, writing Windows GUI apps. X toolkits will give you, like Motif has I think both a C and C++ interface. GTK, which is a toolkit for Linux, has a C bindings. I'm not sure about C++. So the answer is there are bindings to Windows systems, but they're all mix and match. They're not part and parcel to the language itself. Similarly, all the network stuff that you have in Java is not part of the language, so you have to get at that by basically low-level calls to the operating system itself, which is why it's a lot more difficult to use than it is. The other thing, if you ever get involved in C and C++, storage management, storage management, storage management. Especially in C, where you don't have constructors and you don't have new, you spend a lot of your time, every time you make up one of these virtual data types that you're thinking about as classes, you first have to write the equivalent of a constructor and the equivalent of a destructor, all by hand using calc and assembling stuff. And you spend a substantial amount of your time just doing storage management, which Java saves you from, but it's a fixed cost. And in return, you can get something that will run extremely fast. C is wonderfully tunable to various architectures just because you have such low-level control over the memory layout. You have direct control over the organization of arrays and what you put where, and so you can do things that really do make a difference. Okay, tomorrow I am hoping to have show and tell, and we will do layout and jar files and packages, and then we'll go on to web stuff later in the week.